Hello there. We're going to talk a little bit about nutrition. Your current chapter or beginning of Wilkins actually talks quite a bit about the interaction between pulmonary health and nutrition. And you guys know that if you're not nutritionally sound, your body is not going to be able to function as it needs to. We need nutrition to be able to breathe. We need nutrition to be able to move. We need nutrition to be able to do all the things that keep us healthy and help us with our immune systems and things along that line. So there's a very close relationship between respiratory function and disease. You know, folks who go on starvation diets, when they come out at the end of the period, they're very almost cachetic if you look at them, and they have sometimes pulmonary issues because surfactant is gone. They have some immunocompromised other things going on with their lungs, and they really need to be able to eat and get that nutritional help back into their body to help them to heal and then move forward. Food is required for anything that you do. Not all food, though, is equal. You guys know that. If you think about it, a bag of potato chips is not necessarily the same as eating a good sandwich with some organic meats or something along that line. So not all food is equal in its effects it's going to have on the body. There's a really cool book out by Reader's Digest called Foods Heal and Foods Harm, and it goes through the various foods that we have, and it tells you a little bit more about them and what they can do for you. And the amount and type of food that you eat is going to affect your oxygen needs and your CO2 production. These two are very closely related. We're going to talk about what we call the respiratory quotient. And the respiratory quotient basically is how well are you eating at this particular point. Your book has changed a little bit on these. It's not a big deal as long as you understand, because some of the questions in the back of the books are still the same questions they asked in the previous editions. So remember, with breathing and eating, there's a couple of questions, and I'm going to give these to you. Where does air and food enter the body? And most of you guys should know where that is. Where do they enter separate tracts in the body? Where do they meet again in the body? And why are food and O2 necessary at the cellular level? And what is adenosine triphosphate? You know, that's something that I know you guys all know and remember what it is. So one of the things we talk about is metabolism. Remember, metabolism is the breaking down or the building up of our nutrients, okay? And one of the things I should have probably said at the beginning is we have macronutrients and we have micronutrients that we need. Your macronutrients are your carbs, your proteins, your fats, okay? Your glucose, your amino acids, and your lipids. Your micronutrients are your vitamins, your minerals, things that we need a very small amount, but if we don't have it, that's going to cause us some issues. So metabolism is the process of breaking it down, which we call catabolism, or building up, which is anabolism. And one of the things when we start to talk about proteins is that we don't store proteins in the body. We have proteins that we have to eat, and we'll talk about those. And from these proteins we break down, we're able to build up the amino acids. Remember, too, that combustion produces body heat. You have to have food for the fuel to be able to do this. And if you didn't have oxygen, there would be no combustion. And therefore, breathing and oxygen, O2, are part of your nutrition, or oxygen are part of your nutrition. So the question comes up is, what is a respiratory quotient? And if you look here, you can see VCO2, and that V, that dot over the V on the CO2 and the dot over the V with the O2. This is the minute production of CO2 based on the amount of oxygen you're using per minute. And normally the amounts we use we produce about 200 mLs of CO2 every minute, and we use about 250 mLs of oxygen to be able to do that. And when you divide the 200 by the 250, you come up with a 0.8. question you have is, well, where do we use this? Why is this important? If you go back to the alveolar air equation, you remember you have all your oxygen on one end of it, and then on the other side is your PaCO2. And you can multiply the PaCO2 by times 1.25, or you can divide that PaCO2 by the 0.8. There's your respiratory quotient. Whichever one you choose is going to work. They're basically the same, okay? Where does the respiratory quotient come in? It basically comes from your diet. You have to make sure that you have the proper amount of oxygen that you're producing, you have to have them are using, and then you have to have the proper amount of CO2 that we're removing. The majority of CO2 in your body is a result of metabolism. You have to meet the body's metabolic needs. That's your respiratory quotient. Normal is 0.8. Carbs is 1. So for every milliliter of oxygen that you're breathing, you're producing 1 milliliter of CO2. When we talk about carbs, when we have patients on ventilators, we used to try to get them off and we would give them carbs because we thought that was what they needed. And we know that they needed some of that for your diaphragm and for the other parts of your body. The problem is 1 is not a good number, okay? It's your respiratory quotient is 0.8. And so what would happen is we would give these guys the carbs, and then they would have to hyperventilate in order to get rid of that excess CO2. And then sometimes they would tire out, and then we had a harder time getting them off ventilators. If you look, you can see fats are 0.7. Well, then it came to us and said, how about if we throw some fats in with those carbs? 1 plus 0.7, that's pretty good. If you divide that by 2, you come up with like very close to 0.8. So by combining those two, we stopped the hyperventilation. We were able to build the muscles back so that people could breathe, and then we were able to get them off the ventilators. Your proteins sit about 0.85, just basically depending on whatever you're reviewing at that particular point. So there's 4 major components of the respiratory system: the neurologic component, the cardiovascular component, the respiratory muscles, and your lungs. And all of these need some form of nutrition to be able to function and work properly. So the book talks a little bit about measuring your needs, your nutritional needs. It talks about, in this case, you're going to see the metabolic rate will dictate your O2 uptake. This is your VO2. You can measure your VO2 in the laboratory at bedside. Most often when we're doing these, we're looking at the BEE, which is your basal energy expenditure. This means that you're at total rest with no stress or anything else. More realistic is your REE, which is your resting energy expenditure. This is something that we can measure at the bedside, and we do this in what we call indirect coulometry. There is a way of measuring your nutritional needs with direct coulometry. A couple of classes ago, which would have been a couple of years ago, we actually had a couple of young ladies that came from DM that actually worked in a lab where they did the actual direct coulometry. And a couple of the folks in the class at that time had that done. So it was really interesting to see how they did it and then talk about it. My understanding, though, is they closed it down shortly thereafter, which was kind of sad. And when we're measuring either BEE or REE, we're looking for your basic energy requirements for the most part. So there it is, definition of them. At rest without stress, there's your BEE or BMR. At rest, there's your resting energy expenditure. We use this in the hospital when our patients are awake and resting. It is about 10% higher than the BEE at that point. And then what we can do when our patients are in the hospital, now we can figure out how much has to be added to the basic. We know what your REE needs are, what kind of nutrition you're going to need, but what if, in this case, you're getting parental anabolic feeding. Well, in order to get you the right amount of nutrition, we're going to add 1.7 times whatever the BEE measures out. Oral anabolic, we're going to do 1.5 times that BEE. Oral maintenance, about 1.2 times the BEE. The thing about this is we only use one factor. We go in there and say, tell me a little bit about this patient. Let's go ahead and take a look at it. Which one of these is going to meet the needs of these patients at this particular point in time? So there it is, exact energy needs. We know that it produces heat. That's how you measure your calories. That's how much you need at that particular point in time. So direct coulometry measures the heat given off in a controlled room, and that's what these young ladies told us. It was a room you went into and you did whatever you were supposed to do, and they could measure the heat being given off at that point. Indirect coulometry, we're going to measure your VO2, your VCO2. The amount of O2 you're using relates directly with your energy creation and the needs that you have. There is a computerized device called a metabolic cart. We used to be able to use this with the Puritan Bennett 7200, which was an older vent. I have not seen this being used with the newer vents, and sometimes I'll ask the folks who are out there, have you seen this? And sometimes they're telling us no, they haven't, but this is a way to go ahead and measure what's going on. Now, sometimes your LTACs, your long-term acute care settings, they will use something like the metabolic cart to determine the energy needs of the patients that they have there. And this is probably one of the reasons why the LTACs are so good at getting patients off ventilators. They have the time and they really put the effort into it, much more so than we did sometimes do in the acute care situation because of how critical our patients are in that acute care setting. So energy is quantified in kilocalories, and there's your definition of a kilocalorie. It's the amount of energy needed to raise the temperature of 1 kilogram of water 1 degree Celsius. Okay. There's a little formula, you're going to see it in here on these next couple of slides, about feeding people. Okay. Approximately every 5 kilocalories that you burn, you have to use a liter of oxygen. So if your VO2 or your oxygen needs is 300 mLs per minute, and we want to know basically how many kilocalories you have, well, the first thing we're going to figure out is how much oxygen are you actually going to be using. So you take your 300 times 60 times 24, and it comes out to 432 liters of oxygen per day. And I'm quite sure most of you guys haven't thought about how much you actually use. It's kind of interesting. Now we know that we have to have kilocalories because kilocalories is how your energy is measured. 5 times your 432 means that you have to have 2,160 kilocalories per day, and that's your nutritional needs. So there's several ways that we can feed you, and basically what we prefer to do is have you eat and use your teeth, okay, in your mouth, if you want to think about it that way, over us using IVs, feeding tubes, different things like that. One of the things you're going to find out when we talk about TPN, that's total parental nutrition, probably the most expensive, worst way to feed you. We have to watch your sugars and things like that because sometimes you'll end up looking like a diabetic. So we can use IVs. It's interesting if you're in the hospital with your clinical situation and somebody's being fed, if they're going to do IVs, sometimes it's the folks who are putting it together, and you'll get a bag of food that has your proteins, your carbs, and your fats in it, and it'll also tell you what other electrolytes and other things that are mixed with it. So if you have that opportunity, take a look at it. So we're going to go back to what we had before. We're going to give our patient an IV solution of 5% dextrose, okay? They're going to need about 3 liters per day, times 3.41 kilocalories per gram, okay? And so they only need 600 kilocalories per day. They're not doing much of anything, laying in bed, vegetating. But anyways, what we do know, this is not good nutrition. It's not going to meet their energy needs. It doesn't have the proteins. It doesn't have the vitamins. It doesn't have the minerals. It doesn't have any hardly anything that this patient really needs except a little glucose. So what happens with this when we deplete our skeletal respiratory muscle masses, things are going to make us much weaker. We're not going to be able to do the things we need to. So for the most part, our blood sugars, which we get from our glucose, our carbs, is maintained in the liver. And as you can see here, that you can deplete this store of glycogens in 12 to 16 hours if you don't replenish it. And then we also convert the proteins and amino acids to sugar once we've used up your glycogen stores. We need to be able to continue doing what we're doing. You got to find the energy somewhere, and that's where we're going to find it. Gluconeogenesis, that's the production of new energy at that particular point. And there you can see we're going to take it from your functional proteins, your muscles, your enzymes, the proteins that aren't stored in the body at that particular point in time. This is where you're going to see that weakness. This is where you're going to see those patients not getting better. So if you have poor protein nutrition, you have lowered albumin levels. You remember albumin is a serum protein. One of its main goals in life is maintaining oncotic/osmotic pressure, which means that we're going to go ahead and keep the fluid in the vessels where it needs to be. If you have decreased albumin levels, what's going to happen is the fluid now is going to go out, and now we're going to start third spacing at that particular point. With the starvation, we have a decreased muscle strength, decreased FEVC, FEV1, decreased DLCO. There's your correlates with a decreased creatinine height index. That tells us that you have a loss of muscle mass. And we're also going to compromise your immune system. Remember, with your serum proteins, you have your gamma proteins, and your gamma proteins are part of your immune system. So that's one thing we want to make sure that we watch. So when you compromise the immune system, it limits your body's ability to fight infections. It increases in extravascular lung water, and there you're going to see your FRC and pulmonary reserve also decrease. So poor nutrition, for the most part, we see a lot of weight loss. We see this in our patients who have COPD. They're in a catabolic state. Things are breaking down. If you look at a patient who has COPD, remember those guys who use a lot of accessory muscles. They have to use a lot of energy to breathe. They're up and we're trying to rehab them, get them on a better diet so that things actually work well for them. However, before they get to that state, sometimes we see them in this catabolic state. Your resting energy expenditure will measure higher in COPD because of this, okay? And what happens is you now have nutrition depletion and malnutrition. When we see that, we're going to see muscle wasting and malnutrition. And basically what we need to do is think about what are we going to do with these folks, because what it does is exacerbates your COPD. You don't have the exercise tolerance. Like I said, we need to get you up and exercising. 6-minute walk tells us that you're getting better. We need to watch what you're eating for your immune function also, so that you don't get sick. We don't want to see these patients who have COPD in the hospital every 3 or 4 months, because that means things are getting worse. And there you see respiratory muscles develop into a hypermetabolic state. As once they get to that point, you have more energy that you have to be using, and you need to be able to feed these folks so they can do that. Remember, one of the things we see with our patients who have COPD is they can't eat a lot of food. If they eat a lot of food, their diaphragm is already resting on the stomach, and now that stomach is pushing that diaphragm up, and it's making it much harder for them to breathe. We see this, and you guys will probably see this when you go out to clinical, that sometimes these folks who have COPD are in there working with them, or they may have called you before they have lunch and ask if they could have a treatment, and in comes this tray of food that could probably feed 3 people, and they're just sitting there looking at it, and sometimes they'll look at you and go, what do you want me to do with this? Because there's no way that they can eat. Where we see this too is, remember, like at Christmas time or Thanksgiving, we have our patients who have, or family members that have COPD. They come over they eat a very big turkey dinner, and next thing you know, they're sitting there going, I can't breathe, I can't breathe, and they can't breathe because there's too much food in their digestive system. So it's hard for them to eat more food. And they actually did this study, it was kind of interesting. It said there are patients who have COPD need 104, more than 140% really, to improve their nutritional status. So what do we do with these folks? How do we teach them to eat? Well, we teach them what's really good that they need to have. And then we teach them, if you can do it, eat smaller meals throughout the day. So instead of 3 big meals, try 5 small meals. Part of the problem that we have with this is that, especially when some of these folks are living alone or living with someone else who has also COPD, it takes a lot of energy to put these small meals together. And so, you try to get them to do as much of it as they can, put it in the refrigerator, and then it'll be available for them. But unfortunately, sometimes they're unable to do that. And sometimes they'll start to prepare a meal, they get too tired, the meal finishes, and they're sitting there going, I'm just too tired to eat. So they're not going to get that energy and the nutrition they can't need at that particular point in time. So we also know that chronic protein malnutrition, you have your decreased morbidity and mortality. Like I said, we start to see these guys much more often than we really want to. And then you have a lot of respiratory infections that go along with it because you've lost your immunoglobulins at this particular point. And then you have a lot of muscle wasting. This does not bode well for folks who have COPD because we need them in order to survive and to live and to be having a longer period of life, is that they have to be able to move. They have to be able to do the things that they need to do. So remember, 70% of the taste of your food is smelling, okay? And people forget that. People who can't smell for some reason, say nasal polyps or something else that's going on with them, it's like eating cardboard. I don't care what one beautiful meal you set in front of them, they just sort of sit there going, yeah, what am I supposed to do with this? We used to see this with our open heart patients when they came out of surgery and they were off the ventilators. We would talk to them and the food would come and they'd sit there going, all of this tastes like cardboard. What are we supposed to do with these? And we had talked to the nutrition and the dietitian, and they basically said, if you can get them to eat their salad, drink their milk, those two things, that's a really good start. And then as they start to get a little bit better and they get their sense of smell back, then they may start eating the other food too. But you got to give them something. You have to make them want to do that. So why don't they eat for the most part, or anybody really in the hospital? Remember, bronchodilators, one of the side effects sometimes is nausea, even though we just deny that and tell them it's something else. Oxygen administration, you don't realize how much of a disturbance it is to have oxygen blowing through your nose and down your trachea. Especially at high levels, very, very disturbing. We go see these patients, if you remember way back in therapeutics, we talked about it. The fact that you go to see these patients and their oxygen's either laying on their head or on the bed or someplace like that. And they'll tell you, the reason I took it off is I want to eat. Okay? Medications, electrolytes. Remember, we have problems with some of our electrolytes like magnesium, malabsorption syndromes, things like that. We'll have problems with those. Intubation, I always like to throw the food down the tube, but we don't want to do that. Unfortunately, sometimes, as you saw on the x-ray at the end of the trauma, sometimes that food is going into the lungs. The only problem is the lungs do not know what to do with the food. There's your food preparation time, and smaller meals will increase your calorie burning. If you're out there making a gourmet meal, you're using a lot of energy. And other things, peptic ulcers, remember there's things you can't eat, shortness of breath, increased work of breathing, financial concerns. What people don't realize sometimes, and I actually had a student who said, I see this, I understand it. Sometimes people living on fixed incomes don't have very much money, and they have to make a decision between having a place to live, eating, and their medications. And sometimes they're sitting there going, I really need my medications because I need to be able to breathe, I need to be able to move, I need to be able to, function and live. And sometimes what they've found out is these people will actually go to the store, and when the cat food or the dog food's on sale, they'll buy that. And they don't have a cat or a dog. They're the ones eating the food. So when we're talking to these folks, sometimes it's good to listen to them because you may find out something like that that's going on. And then you're going to have to figure out, talk with a dietitian and see what's going on with these folks to help them. All of these lead to increased risk of malnutrition. You can blunt the hypoxic drive. They're not going to breathe well. Once you stop breathing well, you're going to use more energy to try to get the oxygen in. Your neurological component is the first one. This drives and controls your ventilation. There it is. Your VCO2 increases your blood CO2 levels, increases the stimulus to the chemoreceptors. Remember, you have both peripheral and central chemoreceptors. Your central chemoreceptors are affected by these CO2 levels. Increased O2 we get by metabolism. We use it for buffering of fixed acids or both. We have the respiratory center electrical activity, which increases your minute ventilation in some instances. And what your neurological component mainly needs is glucose. If you remember, probably back in the 80s and maybe a little bit into the 90s, maybe late 70s, everything was reduced carbs or no carbs. And everybody kept saying, you can't have carbs. If you have carbs, you're going to put all this weight on. They're not good for you. Don't eat carbs, don't eat carbs, don't eat carbs. You couldn't even buy things that you would normally eat because there was no carbs with them. Well, unfortunately, the neurological component in your body doesn't understand that. What it knows is it needs some glucose, and glucose comes from carbs. And there it is. The energy from the glucose maintains your electrical charge across nerve cell membranes. You guys probably remember back in first semester when you AEP, you talked about muscles and nerves and what you needed at that point. Remember, you need depolarization for the action potential, and then once it's finished, you need the repolarization. You have your neurotransmitters. Look at that, guys. Most of them are amino acids or derivatives, okay? Amino acids don't come from carbs. They do come from your proteins. And what they do is they relay that information from neuron to nerve to function, to muscle in order to be able to function, okay? So one of the things we know is the amount and quality of protein affects the sensitivity of peripheral or central chemoreceptors. And what they have found out is if you eat too much protein, you increase your respiratory response to CO2 or the decreased levels of O2. And it also makes the patient too sensitive to partial pressure changes in oxygen and CO2, so it increases your work of breathing. So basically, if you think about this, remember if your CO2 is between 35 and 45, that's normal. Your O2, 80 and above, is pretty normal also. However, say if you're eating way too much protein at this particular point, your CO2 is now sitting at 42 or 43, and the body is sitting there going, ooh, no, this is pretty bad. I want you to start hyperventilating. You wouldn't normally do that because 43 is good. Everybody recognizes it. But in some cases, your protein, too much protein will cause that and affect it. Okay. So this one is, what is glycogen? These are some more questions for you. Where do we store our glycogen? If you have too much protein, what can happen? If you have too little protein, what can happen? Where do we find amino acids? And what is catabolism? That one sort of just went away a little bit, but it's there. So then the next thing we talk about is a respiratory muscle component. This is the pump driving the lungs. This is how we breathe, okay? This is how we either have increased breathing, decreased breathing, all those chemoreceptors, everything like that. So the final stimulus is your CNS system, and it does give you your respiratory rate, tidal volume, all of that stuff that we have talked about before. So energy is required for contraction and rest. And what you need are blood glucose, free fatty acids. Your free fatty acids come from your fat stores, your muscle glycogen. Okay, most of that's ready if you're eating a proper diet. How much glycogen is stored depends on the carbohydrate level in the diet and your exercise. Okay. And one of the things is, as you see at the bottom, exercise muscles store more glycogen than unexercised muscles. So if you're out there and you're exercising, not dieting, but exercising, you're going to have more glycogen to put into your muscles, which is a good thing because remember, if you deplete your glycogen stores, you're going to go after your muscles to get the energy that you need to continue doing the things you are, including breathing. So here's your questions for this one. What's the main muscles of respiration? What is the main energy source for this muscle? What type of muscle, exercise or non-exercise, will hold the most energy stores? Cardiovascular component has something to do with the heart. Okay, remember you need your heart and your vascular system to get blood through the lungs and the body. Remember your blood carries all of your nutrients, your electrolytes, your enzymes, all of that good stuff to the tissues, and then it returns the CO2 to the lungs so that you can go ahead and exhale. So you're going to need protein to maintain and build the heart muscle and the other structural components of the tissue. It's also, protein is almost everywhere, guys. If you remember, I'm sure in A&P, and I know Sam's really good about this, there's proteins throughout your body. Proteins, proteins, proteins. There's like, what, 10,000 proteins. And so it's not surprising to see that they do a whole lot for us. Part of that buffering action, part of our clotting factors, the transport of our lipids and our iron. Remember, you have your serum proteins, your beta and your gamma and your omega, all of those different things. Actually, no omega. But anyways, your other two that you have at that particular point. So the major blood protein is albumin. And the question is where's albumin produced? And most of you are sitting there going, must be the liver. And you are totally correct. It maintains oncotic pressure, pulls the fluid into the vessel, okay? Arginine is your major amino acid, the highest concentration of plant-based proteins. There's like 22 different proteins that you use to be able to have the proteins that you need. 9 of these, and sometimes the books vary on these, are essential proteins. You don't make essential proteins, you have to eat those essential proteins, and then they get broken down and rebuilt into the amino acids that you need, okay? You also need these for nitric oxide. We know nitric oxide, if we give it to you, has problems, causes methemoglobin, things like that. But you also need it to relax the vasculature so that you can get the blood moving, okay? And it's also there with some of your immune system. So nitric oxide in and of itself is a good thing. It's when we give it to you that we seem to cause the problems. So there's the question. There's your oncotic pressure. Where is it produced? Proteins are made up of what wonderful things we just got through talking about. Which amino acid do you have to have for nitric oxide? And where's this found? So carbohydrates are your major fuel for your heart muscle. Carbs is a major source of 2,3-DPG, and I know you guys remember what that is. Phosphorus is also crucial for the nutrients and synthesizing 2,3-DPG. And remember, it's also there to help us use our ATP, okay? Blood sugar levels primarily come from carbs, and they release the stored liver glycogen. You need to control your blood sugar to have proper metabolic functioning. And there's your 2 questions. What is 2,3-DPG, and what does it do for us? And then fat is a major component of all cell membranes. Remember, you have the phospholipid layer, makes up the plasma boundary on the cells. Remember, it's also part of your surfactant, which does really good things for you. and fat source for fuel for heart muscles, especially when your blood glucose level or muscle glycogen is low. So the essential fatty acids, the backbones of your prostaglandins, they help regulate your lipid level, your glucose levels, and your blood pressure. And what they found out, which is really cool, is that if you eat nuts, and it's really kind of interesting because you have different articles. One article basically said, eat the nuts that look like your organs. So if you want to eat something for your brain, eat walnuts because it looks like your brain. The other parts, the other nuts that you see also look like other different organs. But they appear to have antiarrhythmic properties. So they tell folks who have cardiac issues to have like a handful of nuts. They also contain your omega-3 fatty acids. You'll see those in flaxseed and fish oil. We also have omega-6, omega-9s. There's still a lot of debate going on about those. Vitamins and minerals you need to maintain metabolic pathways, the integrity of the cell membranes, antioxidant activities of the cell. You need enough water. Okay, also we're going to talk about that. Your vitamins and minerals are major players in your body enzyme and metabolic systems. And here you have it. Iron is a major mineral of what? And what attaches to it is carried throughout the body. And so here's your water. You got to make sure you have enough for proper circulation. Remember, if you become dehydrated, we're losing that water. Remember that 92% of plasma is water. And if you start using that, you're going to go ahead and increase your hematocrit because you're losing the water from the plasma, and you're going to have problems with clumping of your red blood cells and other problems that go with it, okay? You're not going to be able to clear the waste from the body, and you're also going to have issues with your blood pressure. So there's your phosphates, commonly depleted in patients with COPD. Medications that we have to watch out for, your corticosteroids. Remember, your corticosteroids, if we're given to you, even if you're only using them in the hospital, make you look like a diabetic. And then people start changing your diet for you. We have a lot of folks that are on diuretics, especially those who have congestive heart failure. We have the bronchodilators that contribute to depletions, and really we got to watch your phosphate levels to make sure that things are working. And then there's the recommended daily allowance of your vitamin A's, vitamin C, vitamin E. And unfortunately, because of the problem with eating, a lot of your patients who have COPD are having issues with these because they can't get it into their diet. So the gas exchange component, okay, these are your lungs. And you got to have a good diet for those guys too. You need to have a VQ match. Remember, you can have a VQ match where everything is where it's supposed to be, or a VQ mismatch where things are not working extremely well. So the question is, what keeps your lungs from collapsing? I know you guys know the answer for that one. People who go on starvation diets or not eating appropriately have decreased surfactant, and then they have emphysemic type changes in their lungs. Remember, your surfactant helps you keep those lungs from sticking together. You have to increase your work of breathing if you don't have much surfactant, and then your lungs are also going to become a little bit on the saggy baggy side at that particular point. We need hydration. Because remember, if you don't have moisture, how do you get rid of the mucus that you're producing? If the mucus stays in the lungs, now you have a problem with a potential bacteria and immunocompromised in your system. So you have to have hydration for those. And then you need good nutrition for your smooth muscle function. Macrophages, remember those guys are what keeps your body healthy by eating all those bacteria and everything else that cause you problems. And then we also need it because you need the immunoglobulins in your mucus. So a little bit more about metabolism. This is where you get your energy from food into your ATP. And we know what the energy currency is. Remember, we talked and said there's two pathways. Catabolism, we break it down. Anabolism, we build it up. And catabolism is what produces ATP. We use them in the anabolic pathway for growth and maintenance, and how you actually survive and move through the um, world that we live in. And does your body really need energy? Hmm? Too little food, the body needs to rely on the store energy stores. If you're using your proteins, you're removing them from your functional muscle masses and other things that you need them for. And unfortunately, things aren't going to work well at that particular point. So there you see too little fat and carbs, the body breaks down the protein for your ATP. So here's the question that nobody likes to answer. What happens to excess food energy? And remember, the more fat increases your metabolic cost of moving and breathing. You guys have seen people who weigh 700 pounds. If you watch them on TV, you hear stories about people who weigh 1,000 pounds plus, and they had to go to the hospital, and they had to pull down walls to get them out of their homes and things like these. These folks aren't up and moving that much, unfortunately, and they have more fat, and it's harder for them to breathe. And because they have to be able to use their lungs, and the fat will sometimes weigh upon them. You also have an increased risk of various diseases. When we talk about metabolism, we're talking about 4 major phases: digestive, catabolism. The third phase is your Krebs or citric acid cycle. It's a pretty interesting one. I'll show you a picture at the end. Remember, and depending on the books you read, the final production of ATP, you're either going to produce 26 ATP molecules or 36 major ATP molecules, and I'm showing you 36. The thing you have to remember, though, in order to get those 36, you have to use 2, okay? In order to get those 36 also, you have to have oxygen. If you don't have oxygen, what happens is we take 2 ATPs, we send it through that first 2 stages. We produce lactic acid through anaerobic metabolism and pyruvic acid, and then we produce 2 ATPs. And then we take those 2 ATPs that we just produced to go back through again, have anaerobic metabolism. We produce more lactic acid, more pyruvic acid, and then we produce 2 ATPs. So if you think about this, the net energy production is 0. So this is basically one of the things that you can look at. This is part of your Krebs cycle. You can see the CoA, SACU, all those good things. There you can see the different compounds, how all these go together. Look at that, ADP and phosphate gives you ATP.